Welcome everyone to my another review video on AP Calculus. This is Unit 4 Contextual Applications of Differentiation. So let's talk about derivative in context. Most of the problem on derivative in context is on motion problem. And if you're familiar with physics, you should know all of these. So let's talk about the derivative position. So let's use x for position and derivative position respect to time is equal to the velocity. So the unit for position is meters and the unit for time is seconds. And because the derivative is basically the slope, the unit for the derivative is the y unit divided by the x unit, which is meter per second. And we see that is the unit for velocity. And let's talk about the derivative of velocity. So we got derivative velocity respect to time. That's equal to acceleration. The acceleration is just the rate of change of velocity. And the unit for acceleration is meter per second squared. We see that the unit for velocity is meter per second, and the unit for time is second, and meter per second divided by second is meter per second squared. That is the unit for acceleration. So let's work on an example. Interpret the statement below. The value of derivative of the velocity function v of t in meter per second at t seconds. At t equal to 10, the rate of change of v of t is equal to 14. So what does it mean? Is that the derivative of velocity respect to time. It says the rate of change. At t equal to 10, at 10 seconds is equal to 14. So we can say at 10 seconds, the derivative velocity is acceleration right here. So the acceleration is 14. It's 14. But make sure we need to include the unit. The unit for this is meter per second right here, divided by second, which is meter per second squared. And now let's talk about differentiate related functions. So when the problem is letting you to solve the derivative of an implicit equation, but the target derivative is not respect to one of the variables that's present in the implicit equation, then we are treating all those variables as a function of the variable or the target variable. So let's see what it means. So we have this implicit equation xy equal to 4. And we're given that the derivative of y respect to t is equal to 1. And we need to solve for dx dt at y is equal to 0.5. So we see t is not present in any of the variables here. So which means that x and y are both functions of t. So which means that we need to use the chain rule for both variables to solve for the derivative. So let's do this. X times y, that we need to use the product rule because none of these are scalars. So we can say dx dt multiplied by y plus x multiplied by dy dt is equal to 0. We see the derivative of constant is equal to 0. So let's see. We're solving for dx dt. So now we can isolate dx dt at the left side. So dx dt is equal to negative x dy dt over y. We know what y is. We know what dy dt is, but we don't know what x is. So which means that we have to solve for x in the original implicit equation. So xy equal to 4. We know that x multiplied by 0.5 is 4 because y is equal to 0.5. So x equal to 8. Now we have all the variables to solve dx dt. Let's substitute in all the values. So that's negative 8 multiplied by dy dt, which is 1 given the question, divided by 0.5. That's equal to negative 16. And that is our answer for relative equations. So let's talk about solving related rates. So let's the equation related to the problem. Solve for the expression that leads to the answer. Solve the unknown variables that can be solved using other equations. Then substitute all the values and to solve the value. So what does it really mean? So let's work on a problem. The area of a circle is increasing at a rate of 12 pi meters squared over hour. The area at t0 is 36 pi meters squared. Find the rate of change of the circumference of the circle at t0. So this problem is talking about a circle. It given both area and circumference. So we need to list the equations that's related to a problem. So we see A is equal to 2 pi r. And circumference, actually that's circumference equation, and area is equal to pi r squared. So let's see the givens in the problem. The area of the circle is increasing at a rate of 12 pi meters squared over h. So which means that the derivative of area respect to time is equal to 12 pi meters squared per hour. And the area at t0 is 36 pi meters squared. So we can say the area at t0 is equal to 36 pi meters squared. And we need to find the rate of change of circumference, which means that the derivative of circumference respect to time is unknown. That is the target value we need to find. So let's solve for it. So dc dt, we got the equation for the circumference. Let's take the derivative of it. So dc dt is equal to 2 pi dr dt. We see we're missing dr dt is not given in the problem. So which means that we have to solve it ourselves. And what are the other givens? We got area and the derivative area, which means that we can use one of them to solve for the derivative of radius. Let's use the area. So we know A is equal to pi r squared. We given A is equal to 36 pi. That's equal to pi. We see we're missing r, which means that we have to use the derivative one. dA dt, let's take the derivative of that. That's 2 pi r dr dt. And we are still missing r, so let's use the area one. So 36 pi is equal to pi r squared. So we get r is equal to the square root of 36 pi over pi, which is equal to 6 meter. Now we can substitute the r in and 12 pi in. So let's move it to the side. Let's move it here. dA dt is 12 pi. So that's 12 pi equal to 2 pi r. We just solved for r. That is 6 meter. So times 6, that should be r d here, dr dt. You see 12 pi, you do 12 pi dr dt. So which means that dr dt is equal to 1. And we have all the values. Now we are ready to substitute into this equation here. So dc dt is equal to 2 pi times dr dt, which is 1, which is equal to 2 pi. Don't forget our unit. That is meter per hour. Now let's talk about local linearity. So what local linearity do is that we are using a tangent line. We're using tangent line. We learn in unit 2 to approximate a value. So the equation for tangent line, if you recall, is y minus y0, which is equal to f prime of x0 multiplied by x minus x0 at point x0, y0. So here's a graph. This is the function of f of x equal to square root of x. And this tangent line is at 4, 2. It's tangent to 4, 2. And our goal is to approximate this point, square root of 5. Because square root of 5 is an irrational number we cannot calculate by hand. But by using tangent line, we can approximate this value really well. So approximate square root of 5 using local linearity. So let's see. Let's say our tangent line function f of x minus 2, that's y0. Let's write the point. That's 4, 2. That's equal to f prime of x0. The derivative of square root of x is 1 over 2 times square root of x. So that's 1 over 2 times square root of x. This x value is 4. Multiplying by x minus our x value, which is 4. Now we can simplify this f of x, which is equal to 1 over 4 times x minus 4. And we're plussing 2, which f of x is equal to 1/4 x minus 1 plus 2. So we get f of x for the tangent line is equal to 1/4 x plus 1. Now we just need to substitute 5 for this tangent line equation to approximate our square root of 5. So f of 5 is equal to 1/4 multiplied by 5 plus 1, which is equal to 1.25 plus 1 is equal to 2.25. So that's f of 5, which is approximately equal to square root of 5. If you use a calculator, square root of 5 is approximately equal to 2.236. And it's a really good approximation if you don't have a calculator with you. And our last concept is L'Hopital's rule. L'Hopital's rule is a really powerful tool when you're calculating limits. So here's what it is. When the result of a limit is 0 over 0 or positive infinity over, no, positive plus or minus infinity or plus or minus infinity, which is indeterminate form for AP calculus, there are actually more that you can apply L'Hopital's rule, but for AP calculus, it's only 0 over 0 or plus or minus infinity over plus or minus infinity. Then we take the derivative of numerator and the denominator and solve the limit again. Note that it is possible that you have to apply L'Hopital's rules multiple times to solve for your answer. However, when after applying L'Hopital's rule and your answer become a undefined, but it's not an indeterminate form, which means that your limit does not exist. But keep solving until you get it's not an indeterminate form. So what does it mean taking the derivative of numerator and denominator? Well, so for this limit, you should memorize it is equal to 1. It's from unit 1, but we will solve for it using L'Hopital's rule. So that's equal to the limit of x approaching 0. We're taking the derivative of numerator, so that's sine of x, and we're dividing by the derivative of the denominator, which is x. That is equal to the limit of x approaching 0. The derivative of sine of x is equal to cosine of x. The derivative of x is equal to 1. So really this expression is it can be simplified as the limit of x approaches 0 of cosine of x, which of course is equal to 1 if you just direct substitute cosine of 0. And that concludes my review video for AP Calculus Unit 4. And please like and subscribe my channel, and I'll see you next time.